Okay, what's up, you guys? I wanted to make this video because I've been getting some questions about the missing link and the food for thought number six solutions. So I just wanted to make this video kind of going through all the problems, solving them, talking to you through why we're doing what we're doing, and hopefully making it all make a bit more sense. So I wrote this down here in the top right corner. This is the missing link formula that you were expected to know, and it is that percent of heart rate max is going to be equal to percent of VO2 max plus 28.12 in parentheses divided by 1.28. What these arrows are indicating is that you can rewrite this equation to get the percent VO2 max is equal to percent heart rate max times 1.28 in parentheses, and then that value subtracted by 28.12. It's pretty simple to do. All you got to do is to isolate this VO2 guy. The first thing you do is multiply 1.28 by both sides, and that's how you get this percent heart rate max and 1.28 in the bracket right there. That'll cancel out the 1.28 here on the bottom. And then you're going to subtract 28.12 from both sides, and then that'll leave you just left alone with the percent VO2 max on the left-hand side. And that way, it just makes it easier rather than rewriting the equation every time. You can just know the formula and plug in the values they have to get the answer you need. But let's take a look at number one, and let's see if we can use this formula. So number one is telling us that we have let's say number one, and we'll say A. We have 25-year-old flip this around, this will be easier. Okay, so we have a 25-year-old doing a 1 mile run with a steady state heart rate of 187 beats per minute. And number 1A is asking us what percentage of their VO2 max are they working at? So we have the formula that tells us if we know the percentage of heart rate max, we can get the percentage of VO2 max. But we do not have the units we need. We have a steady state heart rate, which is not percent of heart rate max. To get the percent of heart rate max, we got to divide. And the value we're going to divide that 187 by is going to be her age predicted max heart rate, which for the purpose of this class, I recommend just using the 220 minus age, as it's pretty easy to do off the top of your head, which is going to give us a value of 195 beats per minute. And the general formula you can think of following is percent heart rate max is going to be equal to steady state heart rate over age predicted max heart rate times 100. You want to multiply it by 100 because this guy right here is going to give us a decimal value, and we want to multiply that by 100 to get it in terms of a percent. So if we take those values and we plug them in, we get 187 beats per minute over 195 beats per minute times 100 is going to give us a value of, if I throw that in the calculator, about 95.9% if we round. That's going to be her percentage of her heart rate max that she's working at. Now, again, especially on an exam, I would show the steps of you rewriting this equation to get this equation that we talked about earlier, just so Andrews knows where you're getting the equation from. But once you have it memorized, it's easier just to memorize it, and then you could just plug in the values. So we know that percent VO2 max is going to be equal to, in this case, 95.9 times 1.28 minus 28.12. And if you throw that in your calculator, you're going to find that percent VO2 max is going to be equal to 95.9 times 1.28 minus 28.12. 94.6%. So what we have just figured out is that if we have the parameters of this question, we have a 25-year-old with a steady state heart rate of 187 beats per minute. We were able to find out that she's working at about 95.9% of her heart rate max, per age predicted heart rate max. And if we use the missing link formula and plug in those variables, then we know that she's working at approximately 94.6% of her VO2 max. And again, those values are going to get closer and closer to the same number as they approach 100, but they will only ever be the same number at 100%, meaning you will only be at 100% of your VO2 max and 100% of your heart rate max when values are both 100%. When they start out at lower intensities, they'll be more and more further apart from each other. But as they approach 100, they get closer and closer together. But again, they'll only be the same value at 100%. And if we look at 1B, which is question 1, part B, it's asking us, are they working mostly aerobically or anaerobically? And I would say that this person, unless they are the world's fastest marathon, or excuse me, the world's fastest mile runner, they are working mostly aerobically. That's horrible. You know what I mean, aerobically. Just because we know that anything over 90 seconds is going to be mostly aerobic. Anything between the first 10 and 12 seconds is going to be mostly phosphagen, which falls under the umbrella of anaerobic metabolism. Glycolysis, which is still under the umbrella of anaerobic metabolism, is going to take us through like 90 seconds. Anything above 90 seconds, we're going to be mostly aerobically, definitionally. Let's try problem number 2. So we'll say number 2A. 40-year-old man, so we know that age equals 40, and we know that he has a steady state heart rate of 150. We're going to do the exact same thing that we did. The numbers are just going to be a little bit different. So we have a steady state heart rate. We want to find his percentage of his heart rate max, and we have his age. So we're going to get his age predicted max heart rate and do 220 minus 40 is going to give us 180 beats per minute. And age predicted max heart rate. Emphasis on the predicted part. We're going to plug that into our above formula, where we say that percentage of heart rate max is equal to 150 beats per minute over his age predicted max heart rate of 180 beats per minute. Multiply that by 100. You plug that into your calculator, you're going to find that this is about 83.3%. So we know that percent heart rate max is equal to 83.3%. Now we can take that and we can just throw that into our formula to get the percentage of VO2, where we know that percent VO2 max is equal to 83.3 times 1.28 minus 28.12. And if we do that, we're going to see that 0.328 equals minus 28.12. 78.5% of VO2 max. Same thing we did for number 1. We knew his steady state heart rate. We knew his age, which we used to be able to calculate what percentage of his age predicted max heart rate he was working at, i.e. his percentage of heart rate max. We could plug that into the same formula and get the percentage of VO2 max. And notice what I was just talking about here. There's only about a 1.3 percentage difference between the two values. We have about 95.9% of max heart rate. And we have about 94.6% of VO2 max. So there's only about a 1.3 percentage point difference. And remember what we said, as they get closer to 100, they become closer and closer to the same value. And look at here. We see that we're at a little bit of a lower intensity. We only have 83.3% of percent heart rate max, but we have 78.5% of VO2 max. So we have closer to a 5 percentage point difference between the two values at this lower intensity. But again, if this person were to increase their intensity, those values are going to come closer and closer, approaching the same value until they're only going to be the same value at 100%. Just good to keep that in mind. Okay, let's do 2B. We know that he weighs 80 kg. So we'll say mass 80 kg and relative VO2 max equals 45 milliliters per kg per minute. How many kcals will he burn in a 30-minute workout? Well, if we know what percentage of his VO2 max he's working at, and we know his VO2 max, we know the intensity he's training at. Because what we can do is we can take that 45 VO2 max value, we can multiply that by this value as a decimal, not as a whole number, as a decimal. So we'll do 0.785. And that's going to give us the relative VO2 of the intensity that he's working at as he's working at that steady state heart rate of 150 beats per minute. So if we take 45 and we multiply that by 0.785, we get about 35.3. And that's the relative VO2 the relative oxygen consumption that he's consuming as he runs at that pace where he's getting that steady state heart rate of 150 beats per minute. So now what we can do is we can climb the ladder like we did a lot before exam one. So we know we have 34 milliliters per kg per minute of relative VO2. If we multiply that by his body mass of 80 kg to go up one rung on the ladder, these values will cancel. And what we're left with is 2826. And this is his absolute VO2 in terms of milliliters per minute. We want to go up another rung on the ladder. We want to get this in terms of liters per minute. So we're going to take that 28.26 milliliters value over 1 minute. We're going to multiply that by 1 over 1,000 because we know that there's 1,000 milliliters per 1 liter, which is going to give us an absolute VO2 value in terms of liters per minute of 2.826. And we have one more step. Two more steps. We know, again, if we look at that metabolic ladder, if we want to go up another rung, we know that for every liter of oxygen we consume, we get 5 kcals that we burn. Which means if we take that value and multiply it by 5, 14.13 kcal every minute that he spends exercising at this intensity. And if he's exercising for 30 minutes, he's going to bring, if we just round to a whole number, about 424 kcals. So if he's exercising at that intensity, where he's working at about 78%-ish of his VO2 max, getting that steady state heart rate of 150, if he does that for 30 minutes, he'll burn about 424 calories, assuming he weighs 80 kilograms and he has a relative VO2 max of 45 milliliters per kilogram per minute. Cool. And yeah, I think that looks good. Okay, let's do number 3. And let's do 3A first. Okay. Our parameters are 20-year-old female, and 80% VO2 max. Super, super easy. Because we can just plug it in. We don't have two values that we have to find a percentage of. We're just given the percentage. So if we know that percent heart rate max is equal to percent VO2, in this case 80, what am I looking? Plus 28.12 over 1.28. We plug that into the calculator. We get approximately 84.5% heart rate max. And that's it. We were just given the percentage of VO2 that this woman was working at. We just plugged it in the formula, and that takes care of 3A. Let's do 3B. If her MET max is 10 METs, what is relative VO2 is she working at? Well, we know per the problem that she's working at about 80% of her VO2 max. The percentage of your VO2 max you're working at and the percentage of your MET max that you're working at are the same thing, the same value. Meaning if you're working at 80% of your VO2 max, you're working at 80% of your MET max and vice versa. It's just in terms of how we describe it, where one we're talking about relative VO2 and the other we're talking about it in terms of METs, but scaled to one another, they're going to be the same percentage. So you have two ways that you can solve this. We can just say, okay, if we know she has a 10 met max, and if we go up the ladder, if we go from mets to relative, we know that's going to be about 35 milliliters per kg per minute because we just take 10 and we multiply it by 3.5. We have two ways we can solve this. Again, we say 80% of our VO2 max. Well, let's say 35 per kg per minute. And we want to know what relative VO2 she's working at. We can say, okay, this is her relative VO2. And we know she's working at 80% of it. We want to multiply it by the decimal value, not the percentage, which is going to give us 28. And that's all question 3B is asking us. Now, just to illustrate the point about these being the same percentage value, but just being described differently, we know if we have 8 mets over 10 mets, and we multiply that by 100, that's going to be 80% of her met max. Whereas if we take the relative VO2 of 28 over 35, multiply that by 100, we're also going to get 80% of VO2 max. So they're always going to be the same percentage. They're just described differently, where this one is just in the units of mets, and this one is in the units of relative VO2. But for the purposes of calculations, when you see percentage of VO2 max or percentage of met max, that'll be the same value for between those. It's just in how you want to describe it. Okay, let's do 4. I'm feeling good. Number 4, A. Okay, we have a 70-year-old, and he has a steady state heart rate of 120. What percentage of his VO2 max is working at? This is easy peasy because we've already done it a few times before. We know that age predicted max heart rate is going to be 220 minus age, in this case 150. We can take 120, the steady state heart rate, over our age predicted max heart rate of 150, multiply that by 100, and we're going to get 80% VO2 max. Excuse me, 80% of heart rate max. Ignore me. And what are we going to do? We're going to plug that into the formula that we've already calculated. We're going to say percent VO2 max is going to be equal to percent heart rate max, in this case 80, times 1.28 minus 28.12. And if we do that, we see that about 74.3% VO2 max, as he works at about 80% of his max heart rate. Easy peasy. Okay, 4B. If he's working at 3 mets during his walk, what is the estimated relative VO2? Okay, a little bit of a tricky one, but I'll show you how we'll solve it. So we know this is the percentage of his VO2 max he was working at described in this problem. And now we're given the work rate that corresponds with that percentage of VO2. So we know that 3 mets is equal to 74.3% of VO2 max. And we're being asked to find his VO2 max, his relative VO2 max, which would be 100% of his VO2 max, right? But we don't know what this variable is. I'm just writing A for the unknown variable because I'm going to be doing multiplication. I don't want to write 2 x's next to each other. But you can say this is met value. All we can do is we can set this up like a regular algebra equation where we're trying to find the unknown variable. In this case, we know that A, our unknown variable, times 0.743. Again, because we want to multiply this by the decimal value. is going to give us 3 mets. Because if this is 74.3% of this VO2 max, if we multiply that by the decimal value, we get the work rate. We want to solve for A, so we're just going to divide 743 from both sides, which will cancel out. And we find that A is equal to, if we do 3 divided by 0.743, about 4.04 mets. And if we have the met value of this person's VO2 max, we can get their relative VO2, because if we go back to the ladder, we know that per 1 met, we have 3.5 milliliters per kg per minute. Values will cancel. We get 14.13. And that's how we found that person's relative VO2, given the information we were given. Okay, one more. Let's do it. Let's do number 5A, where we have this person is going to do the treadmill 3 times a week for 30 minutes. There's only one part to this question, which is nice. What steady state heart rate does she need to work at to meet the CDC minimum for met minutes a week? Well, if you recall, the recommended physical activity in terms of met minutes per week for the CDC and ACSM is around 500 to 1,000 met minutes per week. Again, this is asking for the minimum, so we're going to use this lower value. We know we need 500 met minutes every week. And we know she's going to be working at 3 times a week, 4 times 30 minutes. She's going to be exercising at 90 minutes a week. So if we need 500 met minutes, and we know she's going to be exercising at 90 minutes every week, then we can divide that by that. These units will cancel, and what will be left over is the average met value that she needs to be working at for all 90 of those minutes to hit the minimum standards. So if we do 500 minus 90, we get about 5.56 mets if we round. So now we have the met value. And we want to know, and she has an estimated VO2, and she has an estimated VO2 max of 35 milliliters per kg per minute. So if I want to plug this into my missing link formula, I need to find the percentage of her VO2 max, which I can do because I have the work rate she's working at, and I have her relative VO2. I can convert this to 10 mets, because if we want to go down the ladder, we're going to divide this relative VO2 by 3.5 to get 10 mets. So she has a 10 met max. And again, remember percentage of VO2 max and percentage of met max are the same thing. So I can say 10 mets, her met max, over 5.56 mets, the work rate she needs, times 100, is going to give us 55.6% of VO2 max. So she needs to be working at 55.6% of her VO2 max. If she's only going to be exercising for 90 minutes a week, on average, she needs to be working at this percentage value for all 90 of those minutes to hit the minimum met minute per week value given to us by the CDC and ACSM. So what steady state heart rate does she need to work? So what steady state heart rate does she need to work at? So first we're going to plug this into our formula to get the percentage heart rate. And we know that percent heart rate max is equal to percent VO2, in this case 55.6, times, not times, I'm sorry, not 1, 2, 1 for 1.28, divided by 1.28 is going to give us about 65.4%. heart rate max. Okay. And so what we're going to do is, again, we know this person's age. I did not write it down, but she has age is 42. So we can find her age predicted max heart rate by doing 220 minus 42, which in this case is going to give us 178 beats per minute. We take that 178 beat per minute value and we multiply it by this guy, percentage of heart rate max, as a decimal. We're going to get the steady state heart rate we need. Do 178 times 0.654. We round to a whole number. We get that. So this means if she's going to be working at only exercising for 90 minutes a week, her average steady state heart rate should be about 116 to ensure that she's working at a high enough intensity to hit the minimum threshold of 500 MET minutes every week. Cool. I hope that all made sense. Be good to yourself if it takes you a few times to get these, because they're definitely sort of tricky, especially the way the questions are worded. I'm going to be sending out this video. Well, you know if you get this, and then I'll send out this PDF so you guys have the work too. And yeah, just practice going through them. Send me an email or what have you if you have any questions, and just let me know. Cool. Thank you for watching. See you later.